Welcome to Study Loop.
This is the answer to Chapter 17, problem number 51 from the Smith Organic Chemistry textbook. And in this problem, we're asked to use the inscribed polygon method to show the pattern of molecular orbitals in cycloocta tetraene. And so I've drawn the inscribed polygon. And so we need to draw in the molecular orbitals and label them as bonding, anti-bonding, or non-bonding. Okay. And so our three lowest vertices are going to be the bonding. So there's 1, 2, 3. These will be bonding. Then we have two middle vertices that are going to be non-bonding. And then we have the three vertices at the top that will be anti-bonding. Okay. Okay. Indicate the arrangement of electrons in these orbitals and explain why this molecule is not aromatic. Okay. So we need to populate these orbitals with electrons. And so we have 8 pi electrons to put in here. And so we'll fill the lowest orbitals first. So there's 1, 2, 3, 4, 5, 6. So our bonding orbitals are filled. Now we need to put 1 each in the 2 non-bonding orbitals. And so we've done that. Okay. And so, so why is this molecule not aromatic? Okay. So the non-bonding orbitals are not filled. So another way to say that would be unpaired electrons in the HOMOs, the highest occupied molecular orbitals. So unpaired electrons in the HOMOs. You also, although it doesn't really have anything to do with the inscribed polygon method, could say it's an 8 pi electron system. And so by Huckel's rule, we know that that's not going to be aromatic. Okay, so then for C, we're asked to consider the dianion of cyclopenta tetraene. And so if it's a dianion, there are going to be 2 negative charges. And so we're adding 2 pi electrons. And so there are going to be 10 pi electrons in the dianion. So 10 pi electrons. Okay, so that's C. For D, we're asked how are the pi electrons in this dianion arranged in the molecular orbitals? And so I'm not going to draw this all back out, but they would fill the non-bonding orbitals. So, so let's say 1 more electron in each non-bonding orbital. And another way we could think about that is they would fill the highest occupied molecular orbitals. And so that's why the dianion is aromatic. And I believe that is part E. Classify the dianion as aromatic, anti-aromatic, or not aromatic, and explain why. And so, like I just said, it's going to be aromatic. And so you could say it's going to be aromatic because it's going to be a 10 pi electron system. However, in keeping with the spirit of this problem, we should say that the HOMOs are full and no electrons in non-bonding orbitals. Okay, so it's aromatic because it's a 10 pi electron system, and because the HOMOs are full and there are no electrons in non-bonding orbitals. Okay, and so that's all that there is to this problem. It's a review of the inscribed polygon method. So again, I've drawn the inscribed polygon to the left here, populated the orbitals with the 8 electrons of the original molecule. It's not aromatic because there are unpaired electrons in the HOMOs in the original molecule. The di-anion, however, would be a 10 pi electron system. And so actually, I'll just draw those extra electrons in green. So they would go here and here to fill those orbitals. And that would make the di-anion an aromatic system. And that's the answer to chapter 17, problem number 51.